Welcome to this presentation on the conceptual comparison between the T0 model and the extended standard model. My name is Johan. Today, we will explore how these two mathematically equivalent frameworks offer fundamentally different conceptual approaches to unifying quantum mechanics and general relativity. This presentation is based on my research paper, Conceptual Comparison of T0 Model and Extended Standard Model, Field-Theoretic versus Dimensional Approaches, which is available on GitHub. The unification of quantum mechanics and general relativity remains one of the most significant challenges in theoretical physics. Traditional approaches have typically involved extending the standard model or modifying general relativity, often resulting in complex mathematical structures. In this presentation, we'll compare two frameworks that address this challenge, the T0 model, which posits absolute time and variable mass, and the extended standard model, which maintains the conventional notions of relative time and constant mass. What's fascinating is that these frameworks are mathematically equivalent. The scalar field θ in the extended standard model and the intrinsic time field t in the T0 model are related by a logarithmic transformation. Θ of x is proportional to the natural logarithm of t of x divided by T0. Both frameworks predict an identical modified gravitational potential, phi of r equals negative gm divided by r plus kappa times r. This potential naturally explains galactic rotation curves without dark matter and cosmic acceleration without dark energy, albeit through different conceptual mechanisms. The cornerstone of the T0 model is the intrinsic time field, defined as t of x equals h bar divided by the maximum of m of xt times c squared or omega of xt. For massive particles, this simplifies to t of x equals h bar divided by m of xt times c squared. For photons or waves, it becomes t of x equals h bar divided by omega of xt. This field is conceptualized as a scalar field that permeates three-dimensional space. At each point, it defines a local temporal quality that influences how matter and energy evolve. The field elegantly captures wave-particle duality through the Max function, which naturally handles both extremes of physical reality. Heavier particles have faster internal clocks, represented by a smaller t value, while lighter particles and waves have slower internal clocks, represented by a larger t value. The field-theoretic approach maintains the familiar three-dimensional spatial structure without requiring additional spatial dimensions, which provides a natural mechanism for gravitational interactions through field gradients. In contrast, the extended standard model introduces a scalar field θ that modifies the Einstein field equations. This is represented by the complex tensor equation shown on the slide, where g mu nu is the Einstein tensor, kappa g mu nu is a cosmological constant term, t mu nu is the energy momentum tensor, and the remaining terms involve the scalar field θ. The relationship between θ and the T0 model's time field is logarithmic. Θ of xt is proportional to the natural logarithm of t of x divided by T0. Unlike the intrinsic time field, the scalar field θ lacks a clear physical interpretation. It serves primarily as a mathematical device to reproduce the same predictions as the T0 model. One potential interpretation is that θ represents a fifth dimension beyond the usual four dimensions of spacetime, similar to Kaluza-Klein theory, which attempts to unify gravity and electromagnetism. The ESM preserves the conventional notions of relative time and constant mass while modifying the gravitational sector through this abstract scalar field. When we examine the mathematical formulations in detail, we see that both frameworks employ field equations, though they are structured differently. In the T0 model, the field equation for the intrinsic time field is the partial derivative mu of t plus rho divided by t squared equals 0. The gravitational potential arises directly from the logarithm of the time field ratio, phi of x equals negative natural logarithm of t of x divided by T0. In the extended standard model, the field equation for θ resembles a modified Klein-Gordon equation, the partial derivative mu of θ minus the partial derivative of v of θ with respect to θ equals 8 pi g times rho of xt. The key difference is in how these frameworks handle extreme states of matter and energy. The T0 model directly captures the transition between particle-like and wave-like behavior through its elegant Max function. The ESM must handle these transitions through more complex couplings between the scalar field and the energy momentum tensor, which obscures the underlying physics. One of the most elegant features of the T0 model is how gravitation emerges naturally from the intrinsic time field. For a point mass, the time field solution is T of r equals T0 times the quantity 1 minus m over r plus kappa r. The gravitational force emerges directly from the gradient of this field, f vector of xt equals negative gradient of t of xt divided by t of xt. In the extended standard model, gravitation is modified by the scalar field coupling to the metric. While both frameworks predict the identical modified gravitational potential phi of r equals negative gm over r plus kappa r, they do so through fundamentally different mechanisms. In the T0 model, there is a clear physical mechanism: mass creates time field gradients which then affect other masses and energy. In the ESM, the mechanism is more abstract, arising from modified spacetime curvature rather than from temporal properties. In both frameworks, the linear term kappa r, where kappa is approximately 4.8 times 10 to the negative 11 meters per second squared, explains both galactic rotation curves and cosmic acceleration without requiring dark matter or dark energy. When we compare the ontological status of these fields, we see significant conceptual differences. The intrinsic time field in the T0 model has a clear ontological status as a fundamental property of reality that determines how matter and energy evolve temporally. It has a direct physical interpretation, permeates 3D space as a field property, and naturally emerges from the time-mass duality principle. In contrast, the scalar field in the ESM lacks a clear ontological foundation. It serves primarily as an auxiliary mathematical device to reproduce the same predictions as the T0 model. It's an abstract mathematical construct that could potentially be interpreted as a fifth dimension, but it lacks a clear physical meaning and is added to the theory without clear conceptual motivation. These ontological differences highlight why the T0 model offers greater conceptual clarity while achieving the same mathematical results. Its field-theoretic approach provides an intuitive connection to physical phenomena without requiring abstract dimensional extensions. One potential interpretation of the ESM is that the scalar field theta represents a fifth dimension beyond the usual four dimensions of spacetime. This interpretation draws parallels to Kaluza-Klein theory, which unifies gravity and electromagnetism through a fifth dimension. However, this dimensional interpretation faces several conceptual challenges. If theta represents a fifth dimension, it would still need to be quantified as a field permeating our three-dimensional space to explain local variations in gravitational effects. This essentially reintroduces the field-theoretic perspective of the T0 model, but with added conceptual complexity. The T0 model avoids these complications by directly employing a field-theoretic approach within the familiar three-dimensional spatial framework. This approach maintains conceptual clarity while achieving the same mathematical results. A field that permeates three-dimensional space is conceptually simpler than positing an extra spatial dimension, especially when both yield identical predictions. Both frameworks predict a static, eternal universe rather than an expanding one. This represents a significant departure from the standard lambda CDM cosmological model, which is based on an expanding universe. In both the T0 model and the ESM, cosmic redshift is explained through energy attenuation rather than through the expansion of space. In the T0 model, photon energy loss occurs due to interaction with the intrinsic time field during propagation. In the ESM, a similar energy loss is explained through the curvature-based influence of the scalar field theta on light propagation. Both frameworks make identical predictions for several phenomena, including a wavelength-dependent redshift described by the equation z of lambda equals z0 times 1 plus beta t times the natural logarithm of lambda over lambda 0. They both predict a modified CMB temperature redshift relation, the absence of dark matter in galactic rotation curves, and explain cosmic acceleration without dark energy. While these predictions are the same, they arise from fundamentally different conceptual frameworks, highlighting how mathematical equivalence can exist despite profound differences in physical interpretation. In conclusion, while the T0 model and the extended standard model are mathematically equivalent frameworks, they differ significantly in their conceptual foundations and clarity. The T0 model, with its field-theoretic approach based on an intrinsic time field permeating three-dimensional space, offers superior conceptual elegance and intuitive accessibility compared to the extended standard model scalar field, which lacks clear physical interpretation and potentially introduces unnecessary dimensional complexity. It is important to highlight that even when the ESM interprets its scalar field as a fifth dimension, similar to other theories like Kaluza-Klein theory, this fifth dimension ultimately still needs to be treated as a type of superimposed field permeating our conventional three-dimensional space. This introduces a layer of redundancy, as any fifth-dimensional effects must still be quantified and interpreted within our familiar three-dimensional reality. Another key distinction is that the ESM focuses on wave deflection in curved spacetime, whereas the T0 model directly addresses the temporal properties of matter and their variation. The ESM deals with the curvature of spacetime and its effects on wave paths, while the T0 model understands these phenomena as natural consequences of gradients in the intrinsic time field. This comparison underscores an important lesson in theoretical physics: mathematical equivalence does not imply conceptual equivalence. The way we conceptualize physical reality profoundly affects our understanding of nature, even when different conceptualizations yield identical predictions. From a philosophical perspective, when faced with mathematically equivalent theories that make identical predictions, the choice between frameworks becomes a matter of conceptual preference. According to principles of theory selection, preference should be given to the one with greater conceptual clarity and elegance, in this case, the T0 model. The T0 model's field-theoretic approach represents not merely an alternative mathematical formulation but a fundamentally different and potentially more illuminating way of understanding the deepest structures of physical reality. It offers a coherent understanding of the universe without resorting to the abstract notion of an additional dimension that ultimately needs to be reinterpreted as a field extending through our familiar three-dimensional reality.